Welcome back, listeners. Today I'm joined by machine learning expert Sarah D. Hood to dive deeper into this technology that is quickly transforming so many aspects of our lives. Sarah, thanks for being here.
It's my pleasure, Jane. I'm really excited to discuss the incredible impact machine learning is having across so many fields.
Absolutely. Let's start with the basics. What exactly is machine learning, and how does it differ from more traditional, rule-based approaches to technology?
Well, at its core, machine learning is all about extracting knowledge from data. Rather than relying on pre-programmed rules and expert-designed decision logic, machine learning algorithms can learn patterns and make generalizations from large datasets.
So it's a more data-driven approach compared to the older expert systems that used if-then rules, right?
Exactly. The key advantage of machine learning is its flexibility. Instead of needing a human expert to painstakingly code all the rules, the algorithm can learn those patterns on its own by looking at examples.
That makes a lot of sense. Can you give us some real-world examples of how machine learning is being used today?
Absolutely. One of the most ubiquitous applications is in recommendation systems, things like Netflix's movie recommendations, Amazon's product suggestions, or Spotify's personalized playlists. These all rely on machine learning algorithms that analyze your past behavior and preferences to predict what you might like next.
Wow, I had no idea that was powered by machine learning. That's pretty remarkable. What other areas is it being used in?
The impact goes way beyond consumer apps. Machine learning is revolutionizing fields like scientific research, medical diagnosis, autonomous vehicles. Really any domain that involves analyzing and making sense of complex data. Astronomers are using it to discover new planets, oncologists are using it to provide personalized cancer treatments, and so on.
Fascinating. So it's not just consumer-facing applications, but transforming the way research and discovery happens across so many disciplines. That's really impressive.
Exactly. And the best part is, you don't need to be tackling world-changing problems to benefit from machine learning. Even smaller-scale applications can see huge improvements by leveraging these techniques.
That's great to hear. So, what does it take to actually implement a machine learning model? Is it a complex process?
It used to be quite challenging, but the field has advanced so much in recent years. With the right tools and libraries, building a basic machine learning model is actually quite accessible these days. Of course, there's a lot of nuance and complexity involved in designing robust, high-performing models, but the fundamentals are becoming more approachable.
That's good to know. So, is it something that more and more businesses and organizations should be looking into, even if they're not tech giants?
Absolutely. I really believe machine learning is something every organization should at least be exploring, even if they start small. The potential benefits in terms of automation, personalization, and data-driven insights are just too compelling to ignore these days.
Wonderful. Well, this has been a fantastic introduction. I'm really excited to dive deeper into some of the specifics around how machine learning works and where it's heading in the future.
Me too, Jane. There's so much fascinating stuff to unpack here. I'm looking forward to our continued discussion.
Excellent, let's do it. Stay tuned, listeners. Fascinating stuff, Sarah. So let's dive a little deeper into the core mechanics of how machine learning actually works. You mentioned earlier that there are two main types of algorithms, supervised and unsupervised. Can you explain the key differences between the two?
Absolutely. Supervised learning is all about learning from labeled examples, where you have a dataset with known inputs and their corresponding outputs. The algorithm's job is to find patterns in that data and learn how to predict the right outputs for new, unseen inputs.
Okay, that makes sense. Can you give us some concrete examples of supervised learning tasks?
Sure, let me walk through a few. One classic example is handwritten digit recognition, where the input is an image of a handwritten digit, and the desired output is the actual numeric value of that digit. By feeding the algorithm tons of labeled examples, it can learn to accurately identify the zip code digits on an envelope.
Interesting. And what about medical imaging for tumor detection? How does that fit into supervised learning?
That's another great example. In that case, the input is the medical image, and the output is whether the tumor is benign or malignant. But the key is that you need expert radiologists to carefully label a large dataset of images, so the algorithm can learn from those examples.
I see. So the data collection process can be quite involved and resource-intensive for some supervised learning tasks.
Exactly. Whereas something like credit card fraud detection is a bit more straightforward. The input is the transaction details, and the output is simply whether it's fraudulent or not. Your customers will essentially provide that labeling for you as they report any fraudulent activity.
Got it. That makes sense. So the supervised learning examples you've mentioned all have these known, labeled outputs that the algorithm can learn from. How does unsupervised learning differ?
With unsupervised learning, the algorithm doesn't have any labeled outputs to learn from. Instead, it has to find interesting patterns and structure within the input data on its own. A good example would be topic modeling, taking a large corpus of text documents and automatically discovering the underlying themes or topics without any predefined categories.
I see. So the algorithm has to do more of the heavy lifting in terms of figuring out the patterns and insights from the data without that explicit guidance.
Precisely. And while unsupervised learning can be incredibly powerful, it's often more challenging to interpret and evaluate the results, since there's no ground truth to compare against.
Interesting. So in that sense, supervised learning is a bit more straightforward. The algorithm has a clear objective and can be more easily measured. But unsupervised learning has the potential to uncover surprising discoveries in the data.
Exactly. Both approaches have their strengths, and the choice really depends on the specific problem you're trying to solve and the nature of the data you have available. There's no one-size-fits-all solution.
That makes a lot of sense. This has been a really illuminating discussion, Sarah. I feel like I have a much better grasp on the core mechanics of how these machine learning algorithms work and the trade-offs between the different approaches.
Wonderful. I'm so glad I could help clarify those key concepts. Machine learning is such a powerful and versatile field, but there are certainly nuances to understand. I'm happy we could dive into the specifics a bit more.
Absolutely. Well, this has been a fantastic conversation. I'm sure our listeners have learned a ton as well. Thank you again for your time and expertise, Sarah.
It's been my pleasure, Jane. I always enjoy the chance to discuss the fascinating world of machine learning. Looking forward to our next chat.
Sounds great. Until next time, everyone. Fascinating stuff, Sarah. So you mentioned that unsupervised learning is the other major category of machine learning algorithms. Can you give us some more details on how that approach differs from the supervised learning we discussed earlier?
Absolutely, Jane. The key distinction is that with unsupervised learning, the algorithm doesn't have any labeled outputs to learn from. Instead, it has to find interesting patterns and structure within the input data all on its own.
That sounds a bit more open-ended. Can you walk us through an example of an unsupervised learning task?
Sure, let me give you a good example. One common unsupervised learning application is topic modeling, taking a large collection of text documents and automatically discovering the underlying themes or topics without any predefined categories.
I see. That makes sense. So the algorithm has to kind of figure out the natural groupings or structures in the data on its own.
Exactly. And the great thing about unsupervised learning is that it can uncover insights that you might not have even been looking for. The algorithm might surface surprising connections or patterns that a human would have a hard time spotting.
That's really interesting. So it has more of an exploratory, open-ended nature compared to the more directed, goal-oriented supervised learning tasks.
Precisely. But of course, that freedom also comes with some challenges. Without that clear label or target to optimize for, it can be trickier to interpret and evaluate the results of an unsupervised algorithm.
Good point. So how do you ensure an unsupervised model is actually capturing something meaningful, rather than just finding random correlations in the data?
That's a great question, and it gets to the heart of one of the key challenges with unsupervised learning. You really need a deep understanding of the problem domain and the data itself to ensure the algorithm is uncovering useful insights.
That makes sense. So in a way, the human expertise becomes even more important when working with these unsupervised techniques.
Absolutely. You can't just blindly throw data at an algorithm and expect it to magically solve your problem. Understanding the context of the data, the key questions you're trying to answer, and how the unsupervised findings might fit into the bigger picture, that's crucial.
I see. That nuance is really important. So in summary, while unsupervised learning has this exciting potential to surface unexpected discoveries, it also requires a lot more thought and domain expertise to make sure it's actually solving the right problem.
Exactly. It's a bit of a double-edged sword. But when done right, unsupervised learning can be an incredibly powerful tool for gaining fresh insights from your data. You just have to be thoughtful and strategic in how you approach it.
That makes a lot of sense. This has been a really illuminating discussion, Sarah. I feel like I have a much better grasp on the key differences between supervised and unsupervised learning, and the unique challenges and opportunities of each approach.
Wonderful, I'm so glad I could help clarify those important distinctions. As you said, both supervised and unsupervised learning have their strengths, and the choice really depends on the specific problem you're trying to solve. But the common thread is the need to deeply understand your data and its context.
Absolutely. Well, this has been a fantastic conversation. I'm sure our listeners have learned a ton as well. Thank you again for your time and expertise, Sarah.
It's been my pleasure, Jane. I always enjoy discussing the nuances of machine learning, and I'm glad we could explore the contrasts between these two core approaches. Looking forward to our next chat.
Sounds great. Until next time, everyone. Sarah, we've been discussing the high-level concepts behind machine learning, but now I'm curious to dive into the more practical side of things. Can you tell us a bit about the tools and libraries that data scientists and machine learning practitioners typically use?
Absolutely, Jane. One of the key tools in the Python data science ecosystem is a library called scikit-learn. It's an open-source project that provides a comprehensive set of state-of-the-art machine learning algorithms, along with really thorough documentation.
That's great to hear. So scikit-learn is like a one-stop shop for all the core machine learning algorithms?
Yes, exactly. Scikit-learn contains implementations of everything from classic techniques like linear regression and k-means clustering, all the way to more advanced models like decision trees and support vector machines. And the nice thing is that it's all very well documented, so it's easy to get started.
That's really valuable. I imagine having access to all those algorithms in one place can really streamline the development process.
Definitely. And in addition to scikit-learn, there are a few other key Python libraries that are essential for data science and machine learning work. Libraries like NumPy and SciPy provide a lot of the underlying mathematical and scientific computing functionality.
Yes, I've heard of those before. Aren't they used for things like linear algebra and numerical computing?
Exactly right. NumPy in particular is foundational, as it provides the core data structure, the n-dimensional array, that scikit-learn and many other data libraries work with. And SciPy builds on top of that with a ton of additional scientific and numerical routines.
That makes a lot of sense. So you'd really need those lower-level libraries to be able to leverage the higher-level machine learning capabilities in scikit-learn.
Precisely. And then there are a few other important pieces of the Python data science puzzle, like pandas for data manipulation and cleaning, and matplotlib for visualization. Oh, and the Jupyter Notebook, that's a really popular interactive coding environment that a lot of data scientists use.
The Jupyter Notebook, huh? I'm not familiar with that one. How does that fit into the workflow?
The Jupyter Notebook is fantastic for exploratory data analysis and iterative model development. It allows you to mix code, visualizations, and even text all in one interactive document that runs right in your web browser. It's a great tool for sharing your work and collaborating with others.
I see. That sounds really handy. So it helps bridge the gap between the raw coding and the actual presentation of your machine learning results.
Exactly. The Jupyter Notebook makes the whole iterative process of data exploration and model building much more seamless and engaging. You can quickly try out ideas, see the results, and then refine your approach, all without having to constantly switch between different environments.
That's really compelling. It seems like having this suite of well-designed, open-source Python libraries and tools can make a data scientist's life a lot easier.
Absolutely. The Python data science ecosystem has matured tremendously in recent years, and it's now a dominant force in the field. The combination of powerful libraries, interactive development environments, and a thriving open-source community has made Python a go-to language for both industry and academia.
That's fantastic. It's great to see how the tools and technologies are evolving to support the growing needs of the data science community. This has been really enlightening, Sarah. I'm excited to dive deeper into how all these pieces fit together.
Me too, Jane. There's so much more we could explore, from best practices for setting up a productive data science environment, to the latest advancements in areas like GPU-accelerated computing. But I think we've laid a solid foundation here for understanding the key players in the Python machine learning ecosystem.
Absolutely. Well, I'm looking forward to continuing this conversation and seeing how we can leverage all these amazing tools to tackle real-world problems. Thanks so much for your insights, Sarah.
It's been my pleasure, Jane. I always enjoy talking about the technical side of data science and machine learning. Looking forward to our next discussion.
Same here. Until next time, everyone. Sarah, in our previous discussion, we covered the powerful open-source machine learning library scikit-learn, but I'm curious to dive deeper into some of the other core tools and libraries that are essential for data science and machine learning in Python. Can you tell us a bit more about them?
Absolutely, Jane. As you mentioned, scikit-learn is a fantastic high-level library, but it really sits on top of a whole ecosystem of foundational Python packages that enable powerful data manipulation and analysis. Let's start with NumPy. It's one of the most fundamental libraries in the scientific Python stack.
Yes, I've heard of NumPy before. Isn't that the library that provides the n-dimensional array data structure?
That's right. The NumPy array is the backbone of scientific computing in Python. It gives us a highly efficient way to work with multidimensional arrays of data, which is essential for a lot of machine learning and data analysis tasks.
I see. So scikit-learn must rely heavily on those NumPy arrays as its core data structures.
Exactly. NumPy arrays are the fundamental input format for scikit-learn's machine learning models. Being able to represent and manipulate data in this efficient, array-based way is crucial.
That makes a lot of sense. What are some of the other key libraries in the Python data science ecosystem?
Another really important one is SciPy. It builds on top of NumPy, providing advanced mathematical and scientific computing functionality. One of the key things SciPy gives us is the ability to work with sparse matrices.
Sparse matrices? How do those differ from the standard dense NumPy arrays?
Great question. Sparse matrices are a way of representing data that is mostly made up of zeros. Instead of storing all those zero values, sparse matrices only keep track of the non-zero elements. This can be hugely memory efficient, especially for large datasets with a lot of sparsity.
I see. That sounds really useful for certain machine learning applications. So scikit-learn probably taps into SciPy's sparse matrix capabilities as well.
Absolutely. Being able to work with sparse data representations is critical for a lot of the advanced algorithms in scikit-learn. It allows them to scale to much larger problem sizes.
Interesting. What about visualization? Is there a go-to library for that in the Python data science world?
Great question. The de facto standard for data visualization in Python is Matplotlib. It provides a comprehensive set of plotting functions for creating publication-quality visualizations, things like line plots, scatter plots, histograms, and so on.
Yes. I'm familiar with Matplotlib. It seems like a really powerful library for creating high-quality data visualizations.
Definitely. And the nice thing is that Matplotlib integrates really well with the other tools we've been discussing like NumPy and Pandas. You can easily create visualizations from your data stored in those formats.
That's fantastic. So you've covered the core triumvirate of NumPy, SciPy, and Matplotlib, but I understand there's one more key library to discuss?
Yes, you got it, Pandas. This is another essential tool in the Python data science toolbox. Pandas provides a hugely flexible and powerful data manipulation and analysis library, centered around the data frame data structure.
The data frame? Huh? How does that compare to the NumPy and array?
Great question. The Pandas data frame is similar to a spreadsheet or a 2D table, where each column can have a different data type. This makes it much more flexible than the homogeneous NumPy array. Pandas also brings a ton of data wrangling and querying capabilities that are super useful for exploratory data analysis.
That sounds really handy. So, would you say Pandas complements the more numerical and scientific computing focus of libraries like NumPy and SciPy?
Absolutely. Pandas is a great companion to those lower-level libraries, providing a more user-friendly, high-level interface for working with tabular data. It's a critical part of the overall Python data science ecosystem.
This has been really enlightening, Sarah. It's clear that the Python community has developed an incredibly robust and comprehensive set of tools for data science and machine learning. I'm excited to see how all these pieces fit together in practice.
Me too, Jane. There's still so much more we could unpack, like best practices for setting up an efficient data science workflow, or the latest innovations happening in this space. But I think we've covered the key foundational libraries that anyone getting started with Python for data science and machine learning should know about.
Absolutely. This has been a fantastic overview. I feel much more equipped to start exploring these powerful tools and libraries for myself. Thank you so much for sharing your expertise, Sarah. I really appreciate you taking the time to walk me through all of this.
It's my pleasure, Jane. I always enjoy talking about the technical side of data science in Python. I look forward to our next discussion, where we can dive even deeper into how these libraries are used in real-world applications.
Same here. This has been a great conversation. Until next time, everyone. Sarah, we've covered a lot of ground so far in terms of the core Python libraries and tools that power data science and machine learning. Now, I'm excited to dive into a practical example, the classic iris flower classification task. Can you tell us more about this problem and how it can serve as an introductory machine learning application?
Absolutely, Jane. The iris flower classification problem is a wonderful starting point for understanding the fundamentals of supervised learning. It's a simple yet illustrative task that has been used for decades to introduce machine learning concepts.
Fascinating. So, what's the key idea behind this problem? What are we trying to accomplish?
The goal is to build a model that can accurately predict the species of an iris flower, based on measurements of its sepal and petal dimensions. We have a dataset of iris flowers where the species setosa, versicolor, or virginica are already known. We can use this labeled data to train a model to learn the patterns that distinguish the different species.
I see. So we're leveraging the known iris species as the target variable that we're trying to predict. That makes sense as a classic supervised learning task.
Exactly. By training on this labeled data, the model can learn the characteristics that define each iris species. Then we can use that trained model to make predictions on new unseen iris samples.
That's really cool. And what kind of measurements are we working with here? What are the features that the model will use to make its predictions?
Great question. The dataset includes 4 key measurements for each iris flower: the length and width of the sepals, as well as the length and width of the petals. These 4 numerical features serve as the input data that the model will use to classify the iris species.
Interesting. So the model is essentially learning the relationships between these physical characteristics of the iris and the corresponding species. That makes a lot of sense.
Precisely. The sepal and petal dimensions provide a rich set of features that encode a lot of the underlying biological information about the iris flowers. The machine learning model can then leverage these features to discern the patterns that distinguish the 3 species.
I see. And you mentioned this is a classic example used to introduce machine learning. Why is that? What makes it a good starting point?
Few key reasons. First, the iris dataset is quite small and simple, with only around 150 examples and 4 features. This makes it computationally inexpensive and easy for beginners to work with, without getting bogged down in complex data pre-processing or modeling.
That's a great point. Keeping the initial examples simple and manageable is crucial when introducing these concepts.
Exactly. It also happens to be a well-understood problem with clear and interpretable results, which makes it perfect for illustrating the core ideas of supervised learning, model evaluation, and so on. The iris species are also distinct enough that the classification task is reasonably straightforward.
I see. So this iris example can serve as a nice, gentle introduction before we move on to more sophisticated machine learning problems down the line.
Precisely. The iris dataset is a classic benchmark that has been used for decades to teach and test new machine learning techniques. It provides a solid foundation to build intuition before tackling larger-scale, real-world applications.
That makes a lot of sense. I'm really looking forward to diving into this example and seeing how we can leverage the Python data science tools we discussed earlier to tackle this classification problem. It'll be a great way to put all those pieces together.
Absolutely. The iris dataset is the perfect entry point for our exploration of machine learning in Python. I'm excited to see how you approach the problem and the insights you uncover. Shall we get started?
Yes, let's do it. I'm ready to put these tools to work and see what we can learn from classifying iris species. This is going to be a great first step into the world of practical machine learning.
Wonderful. I'm looking forward to our journey through this classic example. Let's dive in and see what we can discover about the fascinating world of irises and machine learning.
Sounds good, Sarah. I'm ready when you are. Let's get started. Sarah, this is really fascinating. I'm excited to dig into the details of the iris dataset and see how we can use it to build our first machine learning model. Can you help me understand the key elements of this problem and how we'll approach it?
Absolutely, Jane. The iris dataset is a classic introductory example in machine learning, and for good reason. It provides a nice straightforward way to illustrate the core concepts of supervised learning and classification.
Okay, great. So, what exactly are we trying to do here? What's the goal of this machine learning task?
The goal is to build a model that can accurately predict the species of an iris flower based on its physical measurements. We have a dataset of iris flowers where the species setosa, versicolor, or virginica are already known. Our job is to use this labeled data to train a model that can then make predictions on new unseen iris samples.
I see. So we're using the known iris species as the target variable that the model will learn to predict. That makes sense as a classic supervised learning problem.
Exactly. The four key measurements sepal length, sepal width, petal length, and petal width will serve as the feature variables that the model will use to make its predictions. The model will learn the relationships between these physical characteristics and the corresponding iris species.
Interesting. And how is the data structured? Can you walk me through the different components of the iris dataset?
Sure, let me dive into that. The iris dataset is nicely structured and contained within a bunch object provided by scikit-learn. It has several key elements.
Okay, that makes sense. So we have this nicely structured dataset with the inputs, the measurements, and the outputs, the species labels, all neatly organized. This should provide a great foundation for building our first machine learning model.
Absolutely. The iris dataset is really well suited for introductory machine learning because it's small, simple, and the underlying problem is quite straightforward. But don't let that fool you. There's still a lot we can learn from working with this data.
I'm really excited to dive in and see what insights we can uncover. Before we get to the actual modeling, though, I'm curious about one aspect you mentioned, the idea of training and testing data. Can you explain a bit more about why that's important?
Great question. One of the key principles in machine learning is that you need to keep your training and testing data separate. The model is trained on the labeled data, but you then evaluate its performance on a different unseen set of samples. This allows you to get an accurate assessment of how well the model will generalize to new, real-world examples.
I see. So we can't just train the model on the entire dataset and expect it to work perfectly on any new iris samples. We need to hold back some of the data for testing to get a true measure of the model's predictive capabilities.
Exactly. Properly separating the training and testing data is crucial for building reliable machine learning models that can perform well in the real world. It's a core concept we'll need to keep in mind as we work through this iris classification problem.
Awesome, that makes a lot of sense. I'm really looking forward to putting these principles into practice and seeing how well we can train a model to identify different iris species. This is going to be a great learning experience.
I couldn't agree more, Jane. The iris dataset is the perfect starting point to dive into the world of supervised learning and classification. I'm excited to see how you approach the problem and the insights we can uncover together. Shall we get started?
Absolutely, let's do it. I'm ready to roll up my sleeves and start building our first machine learning model. This is going to be really fun.
Wonderful. I can't wait to see what you come up with. Let's dive in and see what the iris flowers can teach us about the fundamentals of practical machine learning.
You got it, Sarah. This is going to be a great journey. I'm looking forward to learning from you and putting these concepts into action. Let's do this. Sarah, as we continue our exploration of the iris dataset, I'm really excited to dive into the next step of the process, separating the data into training and testing sets. Can you help me understand the importance of this step and how we can implement it?
Absolutely, Jane. Properly splitting the data into training and testing sets is a crucial step in building effective machine learning models. Let me walk you through the key reasons why this is so important.
Great, I'm really eager to learn more about this. What are the main benefits of keeping the training and testing data separate?
Well, the primary reason is that we need to be able to accurately evaluate how well our model will perform on new unseen data. If we simply train the model on the entire dataset and then test it on that same data, the results will be misleading.
I see. So there's a risk of the model just remembering the training data rather than actually learning patterns that will generalize to new examples.
Exactly. By holding back a portion of the data as a test set, we can get a much more realistic assessment of how the model will perform on real-world samples that it hasn't encountered before. This is crucial for understanding the model's true predictive capabilities.
That makes a lot of sense. So, how do we actually go about splitting the data in scikit-learn? What's the process?
Scikit-learn provides a really handy function called train-split that makes this whole process very straightforward. It takes your full dataset and automatically divides it into training and testing subsets for you.
That's convenient. So, what are the typical ratios used for the training and testing sets?
A common rule of thumb is to use around 75% of the data for training and 25% for testing. This gives the model a substantial amount of data to learn from, while still reserving a meaningful portion for rigorous evaluation.
Okay, that makes sense. And I noticed you mentioned that the train_test_split function also shuffles the data before the split. Why is that important?
Great question. Shuffling the data is crucial to ensure that the test set contains a representative sample of all the different classes or categories in the dataset. If we simply took the last 25% of the data, for example, it might end up containing only one type of iris, which wouldn't give us a true sense of the model's performance.
I see. That makes a lot of sense. Keeping the class distributions balanced in both the training and testing sets is key for getting an accurate assessment.
Exactly. By shuffling the data first, we can be confident that our test set will reflect the same underlying distribution as the full dataset. This helps us avoid any misleading biases in the model evaluation.
Wonderful. This is all really clear now. Before we move on to actually building the model, is there anything else you'd recommend in terms of inspecting the data visually?
That's a great point. Visualizing the data can be incredibly helpful, both for understanding its structure and identifying any potential issues or anomalies. With the iris dataset, for example, a simple scatter plot could give us a lot of insight into how the different measurements relate to the target iris species.
That's a fantastic idea. I'm really curious to see what patterns might emerge when we start looking at the data in that visual way. Shall we dive into some exploratory data analysis next?
Absolutely, Jane. I think taking a close look at the iris dataset through visualization will be a fantastic next step. There's so much we can learn just by getting a feel for the data before we even start modeling. I'm really excited to see what insights we uncover.
Wonderful. Let's do it. This is such a great foundation we've laid so far. I'm looking forward to continuing our exploration and seeing how we can leverage this dataset to build our first machine learning model.
Me too, Jane. This is going to be a really rewarding journey, and I'm glad we're taking the time to thoroughly understand the data and the principles behind model evaluation. It's going to make us much better equipped to tackle this problem successfully.
Absolutely. Okay, let's get started with that data visualization and see what the iris flowers can reveal to us. I can't wait to dig in.
Wonderful, let's do it. This is going to be an enlightening next step in our machine learning adventure. I'm excited to see what we uncover together.
Sarah, I'm really excited to dive into visualizing the iris dataset now that we've laid the foundation for how to properly split the data into training and testing sets. What can we learn from taking a closer look at the data through visualizations?
That's a great question, Jane. Inspecting the data visually can reveal so much about the underlying structure and characteristics of the iris dataset, which can in turn inform our approach to building an effective machine learning model.
Absolutely. I'm particularly intrigued by the pair plot that you mentioned in the previous chunk. Can you walk me through what insights we might be able to glean from that visualization?
Definitely. The pair plot is a really powerful way to get a holistic view of how the different features in the dataset are related to each other, and how they might be able to distinguish the three iris species.
Fascinating. So, what did you notice when you looked at the pair plot of the training data?
Well, the first thing that jumps out is how relatively well separated the three classes seem to be, especially when you look at the sepal and petal measurements. There appears to be a clear clustering pattern that could make this classification task quite learnable for a machine learning model.
That's really encouraging to hear. So you think a relatively simple algorithm might be able to pick up on those distinctions and learn to accurately classify the iris species?
Exactly. That's why I thought the k-nearest neighbors, KNN, algorithm would be a great place to start. It's a pretty straightforward classifier that should be able to leverage those visual cues we're seeing in the data.
I see. Can you explain a bit more about how the KNN algorithm works and why it might be a good fit here?
Sure, happy to dive into that. The core idea behind KNN is that it makes predictions for new data points based on the labels of their closest neighbors in the training set. So for the iris data, if we have a new flower measurement, KNN would look at the, say, three closest examples in the training data and use the majority class among those three to predict the species.
I see. That makes a lot of sense. And since the pair plot is indicating nice separation between the classes, the closest neighbors are likely to have the same label, making the classification pretty straightforward.
Exactly. The visual cues we're getting from the data exploration suggest the classes are well separated, which should allow a simple KNN model to learn the underlying patterns quite effectively. Of course, we'll have to see how it performs on the held-out test set, but I'm optimistic based on what we've seen so far.
That's great. I'm excited to put KNN to the test and see how it handles this iris classification problem. Before we dive into the model training, is there anything else you think is important to point out about the pair plot or other data visualization techniques?
That's a good question. One thing I would note is that while the pair plot is really insightful, it's still a 2D projection of the 4D feature space. So there may be some interesting interactions or relationships between the features that aren't fully captured by this view. But it's still an excellent starting point for understanding the data.
That's a great point. We have to be careful not to overinterpret the pair plot and remember that there could be additional nuances in the higher dimensional space. Good to keep that in mind as we move forward.
Absolutely. Data visualization is a powerful tool, but it's just one piece of the puzzle. Combining these visual insights with the actual model performance on the held-out test set will give us the most complete picture of how well the iris dataset can be learned.
Wonderful. That sounds like a great approach. All right, I'm eager to see how the KNN model performs. Shall we dive into the implementation and evaluation?
Yes, let's do it. I'm excited to see how this first model handles the iris classification task. With the solid data exploration we've done, I'm optimistic we'll get some promising results. Shall we get started?
Absolutely, let's do it. I'm really looking forward to building our first machine learning model and putting all these principles we've discussed into practice. This is where the rubber meets the road.
Fantastic, Jane. I'm excited to see how this plays out. Let's jump in and get the KNN model up and running. I have a feeling this is going to be a really insightful step in our machine learning journey.
Agreed, Sarah. All right, let's do it. Time to put our data exploration insights to work and build that KNN classifier. I can't wait to see how it performs. Sarah, we've done a great job so far in exploring the iris dataset and training our first machine learning model using the k-nearest neighbors algorithm. Now, I'm really excited to see how this model performs on some new, unseen data. What can you tell me about the process of making predictions with a KNN classifier?
That's a great question, Jane. Now that we've trained the KNN model on the iris training data, we can use it to make predictions on new, previously unseen samples. Let me walk you through how that works.
Fantastic. I'm really eager to see this in action. What kind of new data can we use to test out our model?
Well, let's consider a hypothetical scenario. Imagine we found an iris in the wild with the following measurements: sepal length of 5 centimeters, sepal width of 2.9 centimeters, petal length of 1 centimeter, and petal width of 0.2 centimeters. I've put those values into a number py array, just like we did with the training data.
I see. And how do we get the model to make a prediction on this new data point?
Great question. We can simply call the predict method of the trained KNN model passing in this new data point. The model will then use its learned patterns from the training data to determine which iris species this new flower most likely belongs to.
Fascinating. So let's go ahead and do that. What does the model predict for this new iris sample?
Okay, let's give it a try. I'll call the predict method and see what the model comes up with. Python prediction equals knn.predict x_.
That is really impressive. But of course, the true test is how well the model performs on the held-out test set that we created earlier. How can we evaluate the overall accuracy of the KNN classifier?
Great point, Jane. The test set is crucial for giving us an unbiased estimate of how well the model will generalize to new, real-world data. Let's take a look at the model's performance on the test set. Python _pred equals knn.predict x_test.
97% accuracy. That's fantastic. So we can be quite confident that this model will perform well on new iris samples, beyond just the data it was trained on. That's really reassuring.
Absolutely. The high test set accuracy suggests the KNN model has learned the underlying patterns in the iris dataset quite well. Of course, we'd want to do some additional testing and validation to be completely confident, but this is a great start.
That makes total sense. I'm really impressed by how straightforward the KNN algorithm is, yet it's able to achieve such strong performance on this classification task. Do you think there are any downsides or limitations to using KNN that we should keep in mind?
That's a great question, Jane. While KNN is a simple and effective algorithm, it does have some potential limitations that are worth considering. For example, it can be sensitive to the scale of the features, and it may not perform as well in high-dimensional feature spaces. Additionally, as the size of the training set grows, the computational cost of making predictions can become quite high.
I see. That's good to know. So while KNN is a great starting point, there may be situations where more sophisticated models could be warranted, especially as the problem complexity increases.
Exactly. The beauty of machine learning is that there's often no single best algorithm. It really depends on the specific problem, dataset, and requirements. As we progress through the book, we'll explore a variety of more advanced models and techniques that can help us handle a wider range of challenges.
That sounds fantastic, Sarah. I'm really looking forward to diving deeper into the machine learning toolbox and seeing how we can push the boundaries of what's possible with these iris predictions. This has been a wonderfully insightful conversation, and I feel like I have a much stronger grasp on the KNN algorithm and the model evaluation process.
I'm so glad to hear that, Jane. You're really picking up on these core machine learning concepts so quickly. I'm excited to continue our journey and see what other techniques and insights we can uncover. There's always more to learn, but this solid foundation in KNN and model evaluation will serve us well as we explore further.
Absolutely. I can't wait. All right, shall we move on to the next chapter and see what other machine learning magic we can discover?
Yes, let's do it. I'm eager to see what other challenges and opportunities await us. Onward to the next exciting chapter.
Wonderful. Lead the way, Sarah. I'm right behind you, ready to dive in and keep expanding my machine learning knowledge.
Fantastic, Jane. I'm so glad we were able to walk through the KNN model in such detail. Your enthusiasm and curiosity are truly inspiring. Let's keep this momentum going as we tackle the next steps in our machine learning journey. I can't wait to see what we discover together.
Likewise, Sarah. This has been an absolute pleasure. I feel like I've learned so much, and I'm brimming with excitement to see what's next. All right, let's do this. Onward to the next chapter. Sarah, we've really dived deep into the world of iris classification using the k-nearest neighbors algorithm, and I have to say, I'm incredibly impressed with the results we've seen. Can you walk me through the core code that encapsulates the full training and evaluation process?
Absolutely, Jane. Let me share the key code snippet that demonstrates the end-to-end workflow for applying the KNN model. Python x_train, x_test, _train, _test equals train_her split. Iris_dataset. Data, iris_dataset. Target. Random_state equals 0. KNN equals kneighbors classifier. N_neighbors equals 1. KNN.fit. X_train, 1 train.
Ah, I see. So this code sets up the training and test sets, instantiates the KNN model, trains it on the data, and then evaluates its performance on the held-out test set. And the result is that our model is achieving around 97% accuracy. Is that right?
Exactly, Jane. That's the key takeaway. The model is able to correctly classify the iris species in the test set about 97% of the time. This gives us a lot of confidence that the KNN model will perform well on new, unseen data.
That's fantastic. I love how straightforward and intuitive the KNN algorithm is, yet it's able to achieve such strong performance. And you mentioned that this common interface of fit, predict, and score methods is applicable to a wide range of supervised learning models in scikit-learn. Could you elaborate on that a bit?
Absolutely. One of the great things about scikit-learn is that it provides a consistent, easy-to-use API across a wide variety of supervised learning models. The fit, predict, and score methods that we used here for the KNN model are actually the core interface for working with any supervised model in scikit-learn.
That's really useful to know. So regardless of whether we're using a simple KNN model or something more complex like a neural network or a decision tree, we can leverage this common interface to train, evaluate, and apply the model, right?
Exactly, Jane. That's one of the beautiful things about the scikit-learn library. It allows you to easily swap out different models and apply them to your problem, without having to rewrite your entire workflow. The underlying implementation may vary, but the high-level approach remains the same.
That's fantastic, Sarah. It really makes it easy to explore a wide range of models and find the one that works best for your specific use case. Speaking of which, you mentioned that in the next chapter, we'll be diving into a broader set of supervised learning techniques. I'm really excited to see what other powerful models we can uncover.
Me too, Jane. This KNN model has been a great starting point, but as you said, there are many more sophisticated techniques out there that may be better suited for different types of problems and data. I can't wait to explore those together and see how we can push the boundaries of what's possible with machine learning.
Wonderful, Sarah. This has been an absolutely fascinating discussion, and I feel like I've learned so much, not just about the KNN algorithm, but about the broader landscape of supervised learning. I'm truly grateful for your expertise and your passion for the subject.
Thank you, Jane. It's been a pleasure sharing this journey with you. Your curiosity and enthusiasm have been so inspiring. I'm confident that as we continue exploring the world of machine learning, we'll uncover even more amazing insights and discoveries. This is just the beginning of an incredible adventure.
I couldn't agree more, Sarah. I'm so excited to dive into the next chapter and see what other powerful tools and techniques we can add to our machine learning toolbox. And I know our listeners are just as eager as we are to keep learning and growing in this field.
Absolutely, Jane. In fact, I'd encourage all our listeners to subscribe to this podcast and join us on the next leg of our machine learning odyssey. There's so much more to explore, and I can guarantee you'll come away with a deeper understanding and appreciation for the incredible potential of these techniques.
Well said, Sarah. This has been an absolute pleasure, and I'm so grateful to have you as my co-pilot on this journey. Let's keep pushing the boundaries of what's possible, and I can't wait to see what we discover next.
Me neither, Jane. All right, let's do this. Onward to the next chapter. I'll lead the way, and you keep firing those insightful questions. Together, I know we'll uncover even more amazing insights. Listeners, get ready, because this is going to be one heck of a ride.
I'm right behind you, Sarah. Let's go. Thanks, everyone, for joining us on this exciting exploration of machine learning. Be sure to subscribe so you don't miss a single episode. We'll see you next time.
Absolutely, Jane. Until next time, happy learning, everyone. This is Sarah D. Hood signing off.
And this is Jane, signing off as well. Can't wait to see you all again soon. Take care, everyone.